That looks good on our end. Hey, Ning, if you're in there, the Zoom can't hear the meeting.
There we go.
And,
Okay.
this one as well?
Start the video?
Yes.
Okay. Oh, everyone's gonna have that nice look. Okay.
Yeah, no worries.
You know what you can do, actually? Go back.
Go back.
Yeah, go back to your regular. Okay, now go up to this is PowerPoint, right? Or
It's a
is it
keynote,
not?
actually.
Oh, okay, no, you can't do it here. Sorry. Go ahead and do it here.
Yeah, you need to share you. Yes.
Sharing has failed to start. Okay. So I hope you can see and hear me.
Yes, it looks good and you sound good.
And are we recording?
Yes, it's being recorded.
All right, right on time. Well, we're happy to have Preston Kameni visit us today, one of our candidate interviews. And this talk is being live streamed and recorded. Glad to see everybody kind of sort of distancing or masked up. That's good. We're almost out of this thing, but not quite, apparently. So, and then it'll be available later today. The link to the Zoom video will be available later today. If anybody needs to take a second look before they provide feedback at the end of the week. So Preston Kameni is just completing his PhD at Caltech. He'll be defending in May, if not sooner, maybe, but and working on isotope geochemistry, looking at paleoclimates and modern climates and life in general, I would say, through isotope geochem. And his bachelor's degree was at Princeton, and that was in geosciences, but also certificates in environmental studies, planets and life, and also interested in exoplanet habitability. I don't know if you're going to talk about that today at all, but
Not today.
yeah, but if you meet with them one-on-one or in a group, you might also ask them about that topic, because that's pretty interesting in case we have to leave this planet sometime. So with that, welcome, and look forward to your talk. 45 minutes, and
Okay.
then 50 minutes Q&A.
Very well, thank you for that kind introduction, and good morning, everyone. I'm going to start today really just by thanking you for coming to this seminar and for giving me the opportunity to present my research and my future ambitions. So to get started, this photo shows one of the field sites that I'll be talking about today in Western Iceland. And this is the upper valley of the Eyjafjallajökull River system. And I'm going to be talking about what the dissolved chemistry of fluvial systems like this one can teach us about the global carbon cycle. To motivate this work, I'm actually first going to step away from river systems and think about the need for mass balance in the global carbon cycle. And I need my slides to be activated. So what balances Earth's carbon cycle, right? That's the really big question. And the core issue here is that carbon enters the ocean atmosphere system through volcanic and metamorphic processes, and carbon leaves the ocean atmosphere system through the precipitation of marine carbonate. So how is it that that output of carbon is brought into balance with the input? Well, the classic answer is that on geologic timescales, the processes of chemical weathering force a balance between carbon outputs and inputs to stabilize Earth's climate. And in particular, it's long been thought that a temperature-dependent conversion of silicate minerals into carbonate minerals stabilizes atmospheric CO2 over geologic time. And this is called the Yuri reaction that you may have learned about in classes. Now, in this equation, you can see that calcium from calcium silicate combines with CO2 from the atmosphere to form calcium carbonate, sequestering CO2 into a solid phase. However, we now have evidence that the weathering dynamics are much more complicated, and that there are a host of different chemical weathering reactions that occur during the dissolution of rock. Furthermore, this cartoon only shows the inorganic side of the budget, and does not consider the burial of carbon within organic matter, nor any role for the oxidation of previously formed organic matter. Now, understanding all of that complexity of how it is that Earth's surface and oceanographic processes removes the carbon sourced from its own interior is a large knowledge gap in our understanding of Earth's long-term habitability. Because what happens when these fluxes are out of balance? This figure shows the results of a model from Berner and Caldera in 1997. The y-axis is atmospheric CO2 concentration, and the x-axis is model time. The two curves are results for when carbon inputs and outputs don't match. And the point of this plot is to show that over a time scale of only a few million years, even minor imbalances between inputs and outputs can fully deplete the atmosphere of CO2 or result in extremely high CO2 levels. So this tells us that the global carbon cycle is extremely sensitive to even minor imbalances. The problem is that Earth's climate appears to have been mostly equable for the last few hundreds of millions of years. And these issues come to a head when we consider Cenozoic cooling. So this figure shows the oxygen isotope ratio of carbonate over the last 65 million years. And the long-term trend has been interpreted as a cooling of Earth's climate. Now, previously, that cooling has been attributed to enhanced silicate weathering, potentially following the uplift of the Himalayan mountains. However, that modeling exercise showed us that enhanced silicate weathering can easily have pulled all of the carbon dioxide out of the atmosphere. So counterintuitively, the question is actually what feedbacks source CO2 to compensate for enhanced silicate weathering. And several ideas have been proposed in the literature, including reductions in silicate weathering elsewhere or changes in reverse weathering, shifts in the burial or the oxidation of organic carbon, or changes in the amount of sulfide burial or sulfide oxidation. And today I'm going to use geochemical observations from river systems, enabled by recent developments in mass spectrometry, to evaluate the final possibility. That is, I'm going to spend the next 42 minutes talking about the role of sulfide oxidation in chemical weathering. So first, how is it that sulfide oxidation actually impacts CO2? This is the chemical reaction from the aerobic oxidation of pyrite, which produces sulfuric acid. That means it produces protons, sulfate, and it consumes atmospheric dioxygen. Now on its own, this reaction does not release CO2, but the released protons cause a repartitioning of carbon between the ocean and atmosphere. We can also consider a modified form of the reaction where sulfuric acid weathers carbonate mineral directly and releases CO2. So to see that underway, here's a surface plot of atmospheric CO2 levels. The y-axis here, dissolved inorganic carbon, or DIC, reflects the total amount of carbon in the ocean atmosphere system. The x-axis, alkalinity, or ALK, is formally a titration reflecting acid-base chemistry, but is closely approximated by the difference in charge between conservative cations and anions. And it regulates the partitioning of carbon between the ocean and the atmosphere. Now, for either reaction, the impact of sulfide oxidation is to increase CO2. And I've written transiently here because that CO2 rise is only manifest for the duration over which that sulfate accumulates in seawater. Because the modern ocean has a sulfate residence time of about 10 million years, we often think of 10 million years as the approximate time scale over which atmospheric CO2 will increase due to sulfide oxidation. So now that we know a little bit about how sulfide oxidation impacts CO2, we're going to turn towards a schematic of the global sulfur cycle. The ocean is the major fluid sulfate reservoir at Earth's surface, and sulfate is output from the ocean via two primary processes: the formation of pyrite, secondary to microbial sulfate reduction, and the precipitation of evaporite minerals. Those phases then weather, and their isotopic signal is put into rivers. Rivers are thus very useful because they integrate landscape processes. Rivers see through a lot of lithologic heterogeneity. So in the first part of this talk, I'm going to present excerpts from a few studies that I conducted during my dissertation, focused on using fluvial chemistry to quantify sulfide oxidation, ultimately with the goal of understanding how sulfide oxidation, and silicate weathering fits into the relationship between weathering and the global carbon cycle. So first, I'm going to discuss research from a small catchment in Iceland, showing that rivers are indeed faithful reporters of chemical weathering products and can be used to study sulfide oxidation. Second, using a suite of river water samples from Nepal, I'll show that sulfide oxidation fully counteracts silicate weathering in a major tributary to the Ganges, and may have helped to prevent runaway CO2 loss during Cenozoic cooling. Third, I'll then briefly discuss a new computational toolbox that I developed during my PhD, and which uses new numerical tools to improve quantifications of sulfide oxidation and silicate weathering. Those three projects will form the first part of the presentation. In the second part of the talk, I'm then going to turn towards the work that I would lead as an assistant professor here at UT Dallas. And in particular, I'll discuss how we can use a new type of isotope ratio mass spectrometry called electrospray orbitrap instrumentation to quantify key biogeochemical processes, as well as how my research program complements and expands existing efforts within this department and university. So with that roadmap, we're ready to dive into the first study, which takes place in Iceland. Now, when thinking about river sulfur in the context of the global sulfur cycle, one area that requires better understanding is the potential for in-river sulfur transformations. And the reason that we care about this is that we want to use the chemistry of rivers to study which chemical weathering reactions are occurring. Because sulfide and gypsum have very different sulfur isotopic compositions, it would be really nice if we could use the sulfur isotopic composition of river sulfate to diagnose contributions from those end members. However, biological processes in rivers, such as sulfate reduction or sulfate assimilation, can alter fluvial sulfur chemistry. Now, if these sulfur transformations were widespread, they would impact our quantifications of chemical weathering reactions and our understanding of the role of sulfide oxidation in maintaining planetary habitability. The problem is that identifying these types of fractionating processes in rivers is very difficult because most catchments contain multiple weathering lithologies with distinct or unknown sulfur isotope compositions. In this project, we thus went to Iceland because the bedrock is a nearly uniform and isotopically constrained basalt. That is, we went to Iceland, this really small corner of the world and a really small catchment, because we knew the boundary conditions for the weathering system and could thus diagnose non-conservative processes. So in this talk, I'm going to focus on samples from a single catchment, that of the Efrihugudalsa, which is located at the red dot on the left-hand map. And this is a great field site because it's as far as possible from Iceland's primary hydrothermal axis. Now you can see the catchment in the figure on the right, which is only about 170 square kilometers in size. This is a small catchment. We can walk across it in about a day. The Efrihugudalsa is currently a meandering river. It's about 20 kilometers long, and the region was totally glaciated until about 10,000 years ago, as recorded in a sediment core from the lake at the end of the river. So for context, here's a drone image of the catchment, and you can see a few minor meanders in the main stem Hugudalsa, and then the Hugudalsvatn Lake is at the far end of the image. Now turning to the data, this plot shows sulfate delta S34 against sulfate concentration, with the former measured by MC-ICP-MS, a plasma multi-collector method, and the latter measured by ion chromatography, for data that's organized into a few different groupings based on location in the landscape. And just as a quick reminder, the delta S34 value, so the y-axis of this figure, is the ratio of sulfur 34 to sulfur 32 in a sample relative to that same ratio in a standard, -1, and almost always reported in units of per mil. Now overall, the trend in this data is that sulfate delta S34 values are higher at lower sulfate concentrations. And we can imagine that signal is produced by either two end-member mechanisms or their combination. The first mechanism is the mixing of different lithologies, if multiple end members are present, which can generate curvature in this space of delta against concentration. The second mechanism is fractionation during microbial sulfate reduction, which can lower sulfate concentrations while increasing the 34-32 ratio of the residual material. And this happens because there's a slight energetic preference for bacteria to consume 32 sulfur-bearing sulfate relative to sulfur 34-bearing sulfate. So we'd like to evaluate which of these two mechanisms may explain the data. In the plot on the right, I've now cast the observations as delta S34 against fluoride on sulfate, which is a linear mixing space for sulfur atoms. So most of the data fall on a line, which implies two end-member mixing between a low delta S34 and a high delta S34 end member, and I interpreted those as seasonally integrated precipitation and basalt weathering, each of which can also be constrained on the basis of prior work. So based on these findings, unfortunately, that idea of going to Iceland to study just basalt weathering was stymied by the major role of precipitation in this catchment, which sources well over 50% of some of the sulfur atoms in many of our samples. But based on that same mixing dynamic, this led me to conclude that biology does not exert the dominant influence on the sulfur isotopic structure of the Efrihugudalsa. If fractionating processes like MSR are present, they're secondary to mixing effects. So that data came from river water samples, but we can also test the hypothesis by looking at sediment, both suspended in river water and deposited in the floodplain. And to get sediment samples, we used an auger to dig a hole in the floodplain, recorded a stratigraphic section, and then sampled whatever sediment horizons seemed interesting. If chemical variability in the river were caused by biological processes, then we would expect to see reduced sulfur in sediment. To evaluate the abundance and the redox state of sedimentary organic sulfur, I made X-ray absorption spectroscopy measurements across the sulfur K-edge at the Stanford synchrotron radiation light source. So the figure on the left shows a set of normalized fluorescence emissions curves for samples of Icelandic sediment. And what we're actually measuring here is the fluorescence that is released when an inner shell electron in the sulfur atom is excited by an incident X-ray. Because the X-ray energy that's required to excite that 1s electron is a function of the electron density and the coordination environment, different valence states and bonding environments of sulfur have characteristic spectral peaks. So the first thing to notice here is simply that there are peaks at relatively low energies, consistent with the presence of reduced sulfur moieties like disulfide, thiol, and sulfoxide. There are also oxidized peaks corresponding to sulfonate and to sulfate. So on the right, all the data is now plotted as a waterfall plot, where color is the intensity of the fluorescent response. The overall message here is that we find a diversity of redox phases in all sample types, including vegetation, suspended matter, and floodplain sediment. Now, I don't have time to discuss it today, but an EPSL manuscript we published on this site late last year, I fit these spectra to reference materials and then combine those fits with radiocarbon observations in order to learn more about the evolution of organic carbon during storage in floodplains. But for now, these synchrotron data show evidence for a wide variety of different organic sulfur phases within Icelandic sediment. But to determine if those phases matter for the isotopic structure of the catchment, we need to know if those organic phases are abundant and if they're isotopically distinct from river water. This figure now shows sediment delta S34, measured by EA IRMS, and color-coded by the site of sample collection against inverse sulfur content. And the two main things to see here are first that the sulfur contents are quite low, less than about 0.1 weight%, and that the delta S34 values are similar to the main stem river, about 10 to 20 per mole. If organic sulfur were being produced by microbial sulfate reduction, these delta S34 values should either be much lighter than the river, or they should be isotopically comparable to the river, but with a much higher sulfur abundance. This observed combination of low abundance and moderate sulfur isotope composition tells us that biological processes are not overtly influencing the isotopic composition of the system. So if we return to these two explanations of the data, both the dissolved chemistry and the sediment chemistry tell us that isotopic variability is being generated by mixing and not by biological processes like microbial sulfate reduction. Now, as a corollary to that finding, the contributions of our two end members of precipitation and basalt must be extremely variable across this tiny catchment. And to understand that variability, I conducted a topographic analysis of the landscape. So these two pictures show two very different settings within the Yggdrasil zone. And based on a quantitative analysis of landscape shape, I concluded that it's these geomorphic differences that exert the primary control on sulfate delta S34 by regulating the supply of sulfide into the oxidative weathering zone. In reaches that are carved by glaciers, such as the one on the left, valley fill protects the bedrock from weathering, while in fluvially incising reaches like the one on the right, fresh pyrites are continuously exposed for oxidative weathering. So in this system, we're seeing that geomorphology regulates sulfate delta S34. To conclude this section, despite evidence for biological cycling, in the Yggdrasil, dissolved chemistry is a faithful recorder of sulfur weathering dynamics. Moreover, if the dissolved chemistry looks like a conservative mixture of end members, even in this intensely alluvial environment, where we can even identify and quantify organic sulfur phases, we can now feel really good about using fluvial chemistry to diagnose the controls and magnitude of sulfide oxidation in other settings as well. So to return to this outline, I've just shown you evidence that sulfur chemical signals can be well preserved in fluvial systems. Next, I'm going to turn towards a project where I applied these systematics in a place where the geology is much more complicated, and that's in central Nepal. By quantifying sulfide oxidation here, I sought to study the role of Himalayan weathering in Cenozoic climate change. So for many researchers, the uplift of the Himalaya and the development of the Southeast Asian monsoon system are smoking guns for Cenozoic cooling. Furthermore, this is a great region to study sulfur dynamics specifically because prior work has suggested that the Himalaya may host substantial amounts of sulfide oxidation and in many regions, sulfate reduction. So for this study, river water samples were collected within the blue rectangle shown here in central Nepal. And the samples were collected from 16 different sites during both the monsoon and the non-monsoon seasons. And the samples were collected in 2011, which was prior to the Gorkha earthquake and associated landslide. Zooming in on that blue box, this figure is an elevation map of the region showing the locations of samples. The white circles are the 16 sampling sites, and which span about 6 kilometers of elevation. The numbering begins at the floodplain at station LNS1, and then numbers increase moving up into the mountains. Now, in addition to elevation, these samples also span a lithologic transect. So from a geochemical perspective, the Himalaya is largely comprised of 3 major rock packets. Our upstream sites are dominated by one of these packets, the High Himalayan Crystalline Series, or the HHC, which is shown here in red and orange colors. And this is a highly metamorphosed rock suite composed of gneiss and of granite. In our downstream sites, the weathering system is instead dominated by the other 2 rock suites, the Lesser Himalayan suite, which is shown here in blue and purple, and the Titan Sedimentary Series, which is shown in green. Now, the Lesser Himalayan suite includes Precambrian metasediments, dolomites, and black shales, while the Titan Sedimentary Series, or TSS, includes the Phanerozoic shelf carbonates and the shales that formed on the Indian margin prior to the collision with Eurasia. I just want to stress that one of the key components of this study is the transition from exposure of high Himalayan crystalline in our upstream sites to lesser Himalayan and TSS in our downstream sites. And that transition occurs at the confluence of the Langtang River with the Bodhi-Koshi. So this figure shows the sulfate delta S34 of each sample against sampling location, color-coded by the month of sample collection, and the 34-32 ratio is measured by Neptune at Caltech. And broadly, we can see that delta S34 values break out into 2 groups. The first group are samples from the Langtang River, with sulfate delta S34 values of about 2.5 to 7.5 per mole. Those are the samples on the right side of the plot, from station LNS7 up through LNS16. The second group are samples from lower in the system, from below the confluence with the Bodhi-Koshi, where the delta S34 values were like -5 to 2.5 per mole. Now, relative to that overall spatial variability in isotope composition, annual changes in isotopes at a single site tend to be very muted. That said, along the lower transect, sulfate delta S34 values are lower during the non-monsoon season. But overall, lithology is the dominant influence on the sulfur isotopic ratio of these samples, with a secondary influence from seasonality. So with that finding on the lithologic control, I'm now going to turn towards quantifying the relative amount of sulfide oxidation and silicate weathering. So in quantifying the importance of weathering parameters on atmospheric CO2, it's useful to define 2 new variables called R and Z, which we can calculate through inversion of dissolved river chemistry and plot against one another. R is going to be the fraction of carbonate mineral weathering as opposed to silicate mineral weathering, while Z is the fraction of sulfuric acid weathering as opposed to carbonic acid weathering. And the reason that we care about these parameters is that the ratio of alkalinity to DIC, and thus the impact of weathering on CO2, is a simple function of those variables. An alk over DIC ratio of 2 is a really important reference frame for our considerations, because the ratio of alkalinity, most of the alkalinity that enters the ocean leaves through carbonate precipitation, and that process has an alk to DIC ratio of 2. So as a result, if the weathering system has alk over DIC greater than 2, atmospheric CO2 decreases. If the weathering system has alk over DIC less than 2, atmospheric CO2 actually increases on timescales that are longer than the 5 to 10,000 year timescale of carbonate compensation, but less than the 10 million year residence time of marine sulfate. So when we think only of silicate weathering without sulfide oxidation, we're at R equals 0 and Z equals 0, which underlies the Yuri reaction that we discussed at the very start of the presentation. And when geochemists say things like carbonate weathering doesn't impact the long-term carbon cycle, we're thinking about the x-axis of this space, carbonate and silicate weathering just with carbonic acid. But data can actually plot throughout the space. So this figure shows the results of an inversion of the river data from Nepal in that space of R and Z. And as expected from prior work, we find that most of the weathering is of carbonate mineral. However, we now also find that 10 to 50% of weathering alkalinity is balanced by the consumption of alkalinity during sulfide oxidation. The overall alk-to-DIC of weathering in this system clusters around a value of 2, which is the boundary for weathering to not matter for CO2 over multi-million year timescales. Moreover, the data are close to that boundary for samples from LNS1, which is our most downstream site that has integrated the impacts of all upstream processes. So overall, we actually conclude that weathering in the Narayani River system is not actually impacting CO2 over timescales shorter than about 10 million years, which is the residence time of modern marine sulfur. Okay, so for most of this section, I've been just focused on new observations from the Langtang Trishuli Narayani. But that's really only a small component of the greater Himalayan weathering environment. I'm now going to zoom out a bit and consider data from the entire Ganges catchment. This figure shows the location of previously published data that I've inverted using the same model I applied in the Langtang Trishuli. 3 of these geographic regions, shown in orange, red, and blue, are effectively mountains and mountain front rivers, while the green triangular symbols are samples from the Ganges floodplain. And I'm now going to show these data inverted using the same model in that RZ space, color-coded by data set. So in the Langtang Narayani, we see that most of the prior data is actually in agreement with the new observations, and the new data are shown in blue. So there's again about 60 to 80% carbonate mineral weathering and 10 to 60% sulfuric acid weathering, resulting in weathering that doesn't impact CO2 on timescales less than about 10 million years. So that new finding is replicated through older data. We also see similar results for the other mountain front sites. That said, in the western rivers and headwaters, which are shown in the top right, the data might be shifted towards larger amounts of carbonate weathering and a little less sulfuric acid weathering, while in the Marciandi in the bottom right, there's even more carbonate mineral weathering and even more sulfide oxidation. But in the floodplain, we see a very different story. So here we find low values for the amount of carbonate mineral weathering and much less sulfuric acid weathering. Now, given that these floodplain samples have integrated the upstream catchments, these data are telling us that the inorganic component of chemical weathering, when viewed at the scale of the entire Ganges catchment, nets to CO2 decrease. But overall, in comparing the mountain front sites to the floodplain sites, these data are again showing us the extremely strong control of geomorphology and topography on the CO2 fluxes that are associated with chemical weathering. So to summarize this section, sulfide oxidation occurs ubiquitously in mountainous catchments, but its impact on climate is diluted during passage through the transport-limited floodplains. Now at this point, I've shown you data arguing that we can use river sulfate to study the processes of chemical weathering, and then I've applied those systematics to study Cenozoic cooling. But I really only briefly mentioned the calculations that I did to reach those results. So in the next section of the talk, I'm going to very briefly introduce a new tool that I developed during my dissertation work, specifically to conduct these calculations on dissolved river chemistry. And the name of the tool that I built is Meander, which stands for Mixing Elements and Dissolved Isotopes in Rivers. This tool is on GitHub, and it includes an extensive user guide. So all the work that I produce is open access. Excitingly, multiple groups around the world are already using Meander, and I'm involved with many of those efforts. So the first paper that uses this model that I didn't write came out last week in GCA. Now the question that Meander addresses is, how do you take observations from a river system and turn that into information about chemical weathering and climate? And this ends up being an inversion problem. The challenge is to unmix the river and calculate the fractional contributions of end members. So this is the fundamental equation underlying river inversion, which simply states that the measured elemental or isotopic ratio of river water is a weighted sum of end member contributions. And the challenge is to simultaneously solve a set of these equations for the fractional contributions of end members, so those capital F terms. Now to demonstrate how Meander improves on existing inversion techniques, I'll now describe how I expanded each of these variables. So first, by using a built-in dictionary of common elements and isotopes, Meander can model fractionating processes. Second, using custom cost functions allows for better representation of elements at low abundance, such as trace metals in rivers, and improves the efficiency and the accuracy of the calculations. Third, Meander automatically tracks and calculates the chemical composition of weathering materials. This is analogous to updating your posteriors, which enables the types of spatial analyses that I conducted in Nepal. Fourth, by expanding the set of variables used in normalization, we can now model heterogenic organic carbon oxidation, sulfide oxidation, and even carbon degassing as independent end members. And it helps to avoid probabilistic artifacts that were present in prior inversions. Fifth, by expanding the inversion framework to include sources and sinks of solutes, we can now reliably quantify clay formation, including clays that form with isotopic fractionation. And lastly, we tackled the issue of how to select good inversion results. So rather than selecting just a fraction of all simulations, such as the best 1%, which doesn't guarantee inversion accuracy, I implemented mass balance criteria that force the inversion results to match within user-specified precisions. So overall, the reason that this tool is useful is because it expands the range of river inversion calculations that are possible. And as one example, although I'm not going to talk about it today, in another project, I applied Meander to a data set of global river observations, quantified sulfide oxidation globally, compared that to silicate weathering globally to think about the role of sulfide oxidation in modulating CO2 at the planetary scale, and then I interpreted what the inversion-constrained isotopic composition of weathering rock teaches us about the global carbon cycle. But that's a different project. So for today, that actually is going to conclude the first part of the presentation, the discussion of some of my prior and my ongoing work. And the main conclusions that I hope I've demonstrated are first, that fluvial sulfur chemistry can be a faithful recorder of chemical weathering dynamics. Second, that sulfide oxidation fully counteracts silicate weathering in a major tributary to the Ganges, the Narayani in central Nepal, but its importance is modulated by silicate weathering throughout the Ganges floodplain. And lastly, the Meander is a new and flexible tool for river inversion calculations. Now, collectively, the overall message of this work, the takeaway point, is that sulfide oxidation, modulated by topography, is a key piece of how we understand the relationship between weathering and climate, and of how Earth maintains stability in the long-term carbon cycle. For the remainder of the talk, I'm now going to turn towards the future and discuss the work that I'd like to conduct here as an assistant professor at UT Dallas. So far, I've focused on using river chemistry and fluvial sulfur isotope ratios as tracers of mass fluxes. However, I really want to emphasize that I'm not someone who is exclusively interested in the sulfur isotopic composition of rivers, but that I work on much broader questions about planetary habitability and global biogeochemical cycles. These are the concepts that underlie a geologic perspective on sustainable Earth system science. And in looking forward, I'm interested in focusing on a slightly different set of Earth's biogeochemical processes, utilizing new types of technologies, new samples, facing new challenges across both the modern and the past. So to come back to this outline, we're now entering the second part of the presentation, and specifically the section about applying a new type of isotope ratio mass spectrometry called electrospray orbitrap analysis to questions in global biogeochemistry. Now, when geochemists talk about isotope ratio mass spectrometers, we're often imagining instruments that look like this. A sample undergoes ionization, ion beams are physically separated by mass, and the ions impact on detectors. However, recent breakthroughs have fundamentally altered how we can make these measurements. And in particular, electrospray orbitrap instruments enable new types of measurements by altering both the ionization and the mass detection components of this picture. So on the upstream side, on the sample introduction side, these new instruments use electrospray to convert analytes into molecular ions. This means that a molecule like sulfate or phosphate or nitrate can now be the actual analyte within the mass spectrometer, rather than having to use a derived product of sulfate like sulfur dioxide or sulfur plus. And because electrospray doesn't rearrange the analyte molecule, the clumped isotope composition of molecules is preserved through the ionization process. So this development means that for the first time, we can investigate the isotopic structure of entire molecules and not only single elements within those molecules. On the detection side, rather than physically separating ion beams, the molecular ions are directed into an ion chamber. The movement of those charges is recorded as a current, which is then Fourier transformed into a mass spectrum. So why would you do this? Well, the reason is that Fourier transforms achieve mass resolutions of between about 100,000 and a million. So 1 to 2 orders of magnitude better than the very best conventional instrumentation that can be bought. This is analogous to resolving and having a detector for every singly substituted and doubly substituted isotopolog of a molecular ion. This is a very exciting time to be an isotope geochemist. So those two developments, molecular ionization and Fourier mass detection, allow us to determine the full isotopic structure of biogeochemically relevant oxyanions like sulfate, phosphate, nitrate, and silicate. And to the best of my knowledge, the underlined isotopologs in red have never before been measured using conventional techniques, but they're possible using existing Orbitrap instruments. So as an assistant professor at UT Dallas, my lab would apply electrospray Orbitrap mass spectrometry to address a wide range of biogeochemical questions. That is, we're going to measure isotope ratios that have never been measured before, and we're going to use that information to quantify key sedimentary and biogeochemical processes. So to illustrate that potential, I'm now going to briefly summarize 3 avenues of research that my students and I will work on over the first 5 to 10 years. And these research themes span critical zone dynamics, marine nutrient cycling, and sedimentary archives, each of which provide a different perspective on the global carbon cycle. We need to understand these different perspectives in order to really unpack the complex and dynamic interactions between the lithosphere, hydrosphere, biosphere, and atmosphere that collectively maintain planetary habitability. Moreover, my prior research and my postdoctoral work span these different areas. That is, my background as a fluvial geochemist, a chemical oceanographer, and an Earth historian provides a really rare perspective on the totality of the global carbon cycle that will let me apply new technology to a wide range of different problems. So the first theme that I'm going to discuss today aligns most closely with my dissertation work, and it's on applying Orbitrap mass spectrometry to understand the climatic influences of permafrost degradation. So this is a drone image of the Koyukuk River in Alaska, which is underlain by discontinuous permafrost. And I'm very interested in these environments because they're rapidly changing due to anthropogenic climate change with attendant shifts in sediment-water interactions and in chemical fluxes. So as one example, I'm currently part of a project studying the Yukon River system. And this figure shows time series data from the Yukon for the weathering ratio of alkalinity to DIC. These data show that the weathering ratio has declined over the last 40 years, favoring weathering that partitions CO2 into the atmosphere. And this trend appears to be consistent with either of 2 hypotheses. So first, increased oxygenation of previously frozen sediment could potentially be enabling massive sulfide oxidation. Second, mining activities could be impacting the weathering dynamics of this system at the continental scale. Orbitrap mass spectrometry, and in particular, the full isotopic characterization of sulfate and other oxyanions in river water, could potentially distinguish between these hypotheses. Now, many of these same dynamics are likely at play throughout the extensive Canadian permafrost environments. As a professor, my students and I will study the chemistry of water and sediment samples from these landscapes in order to evaluate the impact of melting environments on chemical weathering and climate. So to summarize, in this first theme, my group is going to apply this new type of mass spectrometry to quantify sediment-water interactions and the impacts of permafrost melting on climate. But when thinking about biogeochemical processes, we often separate the study of fluvial chemistry from the study of chemical oceanography, drawing a disciplinary boundary at the coastline. In reality, these systems influence one another. Rivers source solutes to the ocean, and marine biogeochemical processes that rely on those solutes impact the carbon cycle. Now, in particular, marine productivity, which is one of the 2 or 3 core engines of the global carbon cycle, relies critically on the recycling of nutrients that are sourced from terrestrial environments. So as a second research theme, my group is going to explore the nutrient dynamics of marine settings. And I'm particularly interested in regions like the Southern Ocean, where this photo was taken, because in these waters, large isotope fractionations can be expressed due to incomplete nutrient utilization. For the same reason, these are areas of the world where carbon fluxes are very large and poorly constrained. So as one example, this figure shows the concentration of nitrate in a section through the Pacific sector of the Southern Ocean, where the x-axis is latitude and the y-axis is depth. The white dots indicate water samples, and these figures show the nitrate concentration and the nitrate plus nitrate delta O18 of those samples. The main signal in these data is nitrate assimilation within the photic zone, which decreases nitrate concentrations while increasing the 18 to 16 ratio of the residual nutrient reservoir. we can imagine that that process of nutrient assimilation also impacts the oxygen isotopic structure of other nutrients, things like phosphate, nitrite, and silicate. But these measurements are currently very difficult to make. Orbitrap approaches can measure these variables routinely and will enable new perspectives on the carbon fluxes that are associated with high latitude nutrient utilization. I'm also interested in pursuing questions related to the clumped isotope composition of marine nutrients. And this is really a frontier field, as there honestly are effectively zero measurements for most of these variables. So to summarize those thoughts, in this second theme, my group is going to use novel isotope analyses to quantify nutrient cycling and marine productivity, particularly in high latitude regions. For the final theme, we're going to turn towards the rock record. And the reason for this is that sedimentary archives, in recording the history of climate on Earth, also record how the various components of the climate system interact to maintain planetary habitability. I'm interested in whether there are lessons within that narrative that could either contextualize or potentially be brought to bear on issues of modern climate change. And to motivate this work, consider this figure showing the carbon isotope composition of carbonate rocks during the Cambrian. You can clearly see that the C13 to C12 ratio of these materials goes up and down through time. These types of features are not unique to the Cambrian, but they seem to be a mode of signal preservation throughout at least the Phanerozoic and the Proterozoic. That is, the Earth makes these carbon isotope variations, and this is telling us something about paleoenvironmental conditions. Now, previously, these signals have been interpreted as instability in the global carbon cycle. However, recent evidence shows us that carbonate delta C13 is not always a record of global seawater chemistry, but may instead reflect the influence of local processes, such as marine diagenesis. So as one example, here's a figure from a recent modeling article that shows that during the course of diagenesis, both the carbon and calcium isotope ratios of a primary mineral can be hugely modified. To say that another way, this means that we might not be correctly interpreting the information content of carbonate rocks. My group is going to interpret chemical sediments within a diagenetic framework by measuring calcium, magnesium, sulfur, and uranium isotope ratios in both carbonate rocks and fossils. That is, we're going to work on the very basic question of how to interpret these carbonate archives in order to gain insights that we can apply to the future. So turning to this overview, I hope that I've motivated some of the work that I'd like to lead here as an assistant professor and convinced you that new instrumentation will allow us to tackle some really important biogeochemical problems across modern landscapes, marine settings, and the geologic past. Now, for the last section of the talk, I'm going to address the question, why UT Dallas? Right? What part of this research really complements this particular institution? So first, the Natural Science and Engineering Lab here at UT Dallas already has a really rich set of analytical tools and physical infrastructure, including clean labs and a Center for Mass Spectrometry that houses a GCMS, a Q-top, and a multi-top instrument. By adding Orbitrap mass spectrometry to that list, I can help bring UT Dallas to an even higher level of analytical excellence. Now, second, the range of my interests and my abilities will form the basis for many productive collaborations, both within the Department of Geoscience, as well as across the university and with faculty at neighboring universities. And I'm motivated to work with the other new faculty that would sort of come in as part of this cluster hire. That's very exciting to be part of a new cohort. And then lastly, Dallas is a great location for this work. There's easy access to important river systems like the Brazos and the Mississippi, as well as access to marine sites via the Gulf, and a lot of really interesting Phanerozoic rocks to work on nearby. Now, from a teaching perspective, I'd be happy to lead a wide variety of different undergraduate and graduate courses here. I've highlighted a few existing courses that I could teach, such as history of Earth and life, the global environment, the Earth system, and hydrogeology and aqueous geochemistry. But I'm also interested in offering new courses focused on topics like the interactions and emergent behaviors of biogeochemical cycles, stable and radiogenic isotope analysis, which would include making measurements in my lab and using instrumentation throughout the university. I'm also interested in teaching a class on connections between fluvial landscapes and the global carbon cycle, chemical and biological oceanography, and of course on isocores and marine sediment. Now, within those courses, I think that research projects can be a very useful tool for exciting and engaging students. And this is moving away from the idea of a course as a specific set of facts that need to be communicated, and towards the idea of a course as an active learning, inquiry-driven environment that can help students find their own interests and meet the goals that they're setting for themselves. Moreover, the evidence is really in that these inquiry-driven approaches can result in much more equitable classroom outcomes, and they help to reduce some of the racial disparities that are currently plaguing this field. So as one example, these images are from a student that I mentored who collected vegetation samples from a local arboretum and then measured sulfur isotope ratios in those samples to look for phylogenetic relationships. Now in the process, they learned much more about plants and isotopes than if they had just attended lectures. So for a class in isotope geochemistry, a natural extension of that arboretum project would be for students to rediscover the difference between C3 and C4 plants. For a course on landscape dynamics, we could instead quantify seasonal and long-term changes in river pollutants. For a class in biogeochemical cycles, we could build isotope-enabled numerical box models. Moreover, as an assistant professor at UT Dallas, I would embed equity-minded approaches into my teaching in addition to research and service. So in general, white scientists are hugely overrepresented in the percentage of degrees received, and historical data shows us that that ratio is not changing favorably. DEI initiatives are critical for addressing those inequities, not just in race, but also in the representation of different gender identities and socioeconomic backgrounds. Furthermore, the data are clear that diverse perspectives translate into better research outcomes. So while at Caltech, I've been part of several programs that increased accessibility and inclusion. First, I made a very large effort to seek diverse candidates when organizing a weekly seminar series. And over the course of a year-long program, more than 95% of our speakers identified as women. Now, one outcome of that effort was that students reported feeling more welcome in the department by knowing that there would be at least one female speaker each week. Second, I participated in URGE, which is Unlearning Racism in the Geosciences, which was a series of readings and discussions focused on restructuring the policies of our department to promote inclusion and belonging. And at the end of that program, I became the inaugural liaison between the geochemistry graduate students and our department's DEI committee. Third, I've also been very involved with outreach activities. I organized 2 seminar series in local schools, many with high enrollment of Hispanic students, and I delivered lectures on high-latitude fieldwork and global biogeochemical cycles. So I intend to continue and expand those efforts here at UT Dallas. First, I'd like to offer flexible undergraduate research opportunities during both the summer and the academic year. I'd also be happy to join or lead department discussion groups and attend trainings to ensure that all students are able to thrive in our classrooms, our labs, and on field trips. And lastly, I'm excited to participate in outreach activities through partnership with the Department of Community Engagement and to work with local educators to develop open access lesson plans on the global carbon cycle in both English and Spanish. And that brings me to the end of the talk. So in conclusion, looking back on my dissertation work, sulfide oxidation is part of the relationship between weathering and climate, and it appears to be a critical component of the modern and ancient global carbon cycles. Moving forward, there are really exciting opportunities to study biogeochemical processes and the global carbon cycle using both novel instrumentation and existing infrastructure at UT Dallas. I'll just finish by acknowledging my funding sources, by acknowledging that this work wouldn't have been possible without the support of many graduate students, postdocs, lab managers, and faculty advisors. Lastly, I'd like to thank you for listening and for providing this opportunity to visit the department. So thank you again, and I'm excited to take your questions.
Great, we can open it up for questions.
How many hours a week do you work?
Sometimes when the mass spec is working great, more than you still should be. I don't know.
While they're thinking, I've got a question. So in your inversion, that interests me. It looked like it was a linear inversion, is that right? But are some of the parameters under the summation series, are some of them functions of each? Any non-linear connections between some of those parameters?
Yeah, so one of the key parts of the inversion is the term that you use to normalize. And the problem for that is that river waters are measured in units of concentration, right? They're normalized by liters typically, whereas the measurements that we make of rocks are normally in sort of ppm units, right? And there's this trouble of how do you actually take a solid material and turn that into a concentration measurement. So the way that we do that is by comparing moles to moles. So you need to choose a normalization value. So traditionally that's been done with sodium. And the problem with using sodium is that sodium is not in all N members. Right? So for example, we've typically just chosen that carbonate N members are going to have a calcium to sodium ratio of 60. And that's not a very good assumption because you can end up sourcing quite a bit of sodium from a carbonate end member, and that doesn't make sense. So one of the big innovations in the last couple of years was to realize that you could use sums of different dissolved concentrations in that normalization variable. And what that does is it makes that normalization a function of the concentration of everything else. Yeah. So what had been done before was using the sum of cations, so calcium, magnesium, sodium, and potassium. And one of the big innovations in Meander was adding sulfate and alkalinity actually into that normalization. And what that allowed us to do was model end members that just source sulfate or alkalinity, like pyrite oxidation, whereas previously pyrite oxidation actually had to be folded in to an end member like carbonate or silicate, so you could actually get a cation into the denominator. So there's both nonlinearity in it, and then a second source of nonlinearity can be the cost function that you apply or that you employ. So sometimes we'll do things like normalize by concentration, or you can add in weighting terms as well.
So that nonlinearity, of course, turns into nonlinear inverse problem, which are hard to solve, and there's many ways to try to solve the nonlinear inverse problem. And it opens up, you've got much bigger null space to do with quantitative uncertainty analysis. So how do you explore that space? Because there might be multiple solutions that still fit your.
Yeah, definitely. So this is all Monte Carlo approach. So, and part of the reason for that is that there's a lot of chemical heterogeneity in end members, right? So when you think about something like the silicate end member of the Himalayan weathering environment, well, that actually isn't one value, it's a huge range of values. It's similar for the carbonate, and that the sort of effective chemistry of each end member may also change seasonally as a particular point in space has exposure to different upstream water fluxes, right? You know,
So Monte Carlo methods, now part of the problem is being sure you sample the tails of the distribution and so forth.
Yeah.
So have you had any issues with that in this particular method?
We haven't. I mean, part of how we've sort of dealt with that is just by accepting a very wide uncertainty envelope. So sort of in the sort of paper that reported this model, we used the 5th percentile and the 95th percentile of the posteriors just to sort of get the full range of possible values. I think that there are probably Bayesian methods or sort of smarter ways to go about it. That'll be Meander V2.
Okay. Yeah, I'm sure it can work vague. All right, somebody else must have a question.
We actually have a Zoom question, if you wouldn't mind. So we have Catherine, who's a PhD student. Catherine, you want to unmute and ask your question? Actually, Catherine, there's something wrong with your audio. So maybe you could put it in the chat.
That's a decent question. Maybe you can type it in and you can read it.
Yeah, I think Catherine's going to type it and our speaker can repeat it. And actually, we have some people in the chat that would like you. We can't really hear the questions being asked in the room. So if you could repeat them for them, that would be great.
I knew that.
While they're typing, I think.
No, I just wonder, did you see any signature in your sampling from the dimethyl sulfide from the ocean?
From the what?
Dimethyl sulfide.
Oh, yeah, it's a really good, sorry. So the question was, did we see any evidence of dimethyl sulfide coming out of the ocean? Yeah. It's a good point, right? So more broadly, I'd say, you know, there's this whole class of atmospheric input parameters that we're not necessarily adequately accounting for. So DMS is one of them, but another one's just like anthropogenic pollution. And so for something like the Himalaya, especially in the really upstream regions, we sort of treat those as if they're truly pristine environments. But for that like global inversion that I was talking about, we know that there's about 1.5 teramoles of anthropogenic sulfate sort of in river systems globally. An interesting complexity, though, is that you're sort of talking about, you know, atmospheric sulfur going into the system, but there's another question about sulfur being reduced and then going out of the river systems. So the gas flux could go either way. And part of the problem is that if we were to see a huge, let's say, big increase in delta S34 of river sulfate, and we think that's secondary to something like microbial sulfate reduction, you know, that reduced sulfur, that isotopically light sulfur, it either has to be stored in the catchment somewhere or it has to be degassed out. So things like pyrite aren't going to get transported very far without being oxidized. So a system like Iceland is growing. I mean, it is a place where you could be storing lots of pyrite and we're not seeing it. But for landscapes that appear to be more in steady state, if you go measure the sediment and you don't see really isotopically light material, you can sort of ascribe that to the gas flux out. That said, when folks have sort of tried to measure this H2S flux leaving river systems in places like the Amazon, they haven't necessarily seen it at scale. But certainly I take your point that one of the big steps forward for this work would be doing really robust atmospheric modeling of sulfur transport and deposition.
Okay,
Yeah,
so we have our question in the chat. I'll go ahead and say it for her. Catherine asks, so you mentioned permafrost, but I wanted to know about glacial weathering since it is a source of CO2. Do glacial waters increase oxidation? And can you get information about climate change from glaciers and sulfide oxidation? Or is sulfide oxidation independent of glaciation?
Yeah, so that's a great question. So there's a paper by Torres et al. In 2017 in PNAS that sort of took a huge compilation of glacial and non-glacial rivers, and they ran it through a pretty similar inversion model. And what they found was that glacial rivers definitely have a tendency to oxidize sulfide more readily than non-glacial systems. So it's certainly the case that, at least based on existing data, it looks like glaciers do have a tendency towards sulfide oxidation. Now, the reason for that is typically attributed to the fact that glaciers are hugely erosive. So they generate an enormous amount of sort of fine-grained particles that are very susceptible to weathering. So if you have a system, glacial flow. So if you have that system, you can generate really rapid pulses of sulfide oxidation. I think there's interesting questions, though, about the long-term behavior of that system. Right? So if you sort of imagine that you have a mountain, and that mountain will ultimately be weathered to nothing, you can either do that over some amount of time, or you can speed up that process with glaciers. Right? So there's both processes will result in the same amount of sulfide oxidation in net, because you're going to remove all the sulfide in the system, but one may do it faster. So that's sort of a long way of saying, like, yes, glaciers do increase sulfide oxidation when we observe it. And I think there's interesting timescale dependence in the question.
Okay, thank you.
Great talk, thank you so much. I really enjoyed it. And we mentioned about the teaching part, and especially very interesting in your future strategy to teaching something about Earth system, because a lot of your research is about cycles, energy transfer, and I really think this Earth system concept is one of the very challenging but key points for the future of geoscience education. Do you have any kind of specific preference? I know you want to do inquiry-based education. That's really good part. Do you have any other kind of strategies you think would be effective and you want to use in the teaching?
Yeah, I mean, so I can tell you just a little bit. I mean, I've mentored a bit and I've taught a few courses as a graduate student. I'd say the largest lesson from that is that, teaching is a real skill and you have to work on it. And I've started working on that sort of by taking a teaching class at Caltech. I earned sort of a certificate of interest in STEM education, but there's a pretty long road to go, right? So, it seems like UT Dallas has teaching college. There's this UTeach program that I hope everyone's doing. There's the Center for Teaching and Learning. So as an instructor, I want to sort of engage with those programs to become a more, effective teacher. To sort of, I'd sort of summarize it by saying I'm going to be someone who uses evidence-driven pedagogy and inclusive pedagogy. Right? So I'm all for sort of transparency in learning and teaching, telling people why they're doing assignments, what I'm hoping they're going to gain from it. And also, everyone is trying to sort of meet the goals that they're setting for themselves, right? I'm not trying to give people problem sets because I care if they do the problem set, or it's because I think that it's sort of a useful activity to achieve a particular outcome. So if people aren't, sort of fired up about the work, we should be rethinking what work it is and how we can redesign that work to help students get where they want to go.
Yeah, also, since you already done this, I think it's kind of developing a software to help people to do their immersion data processing. I think maybe you can also contribute some of the computer science programming and data analysis skills into the course. Maybe some courses can be very useful for us in the future to dealing with using your modeling skills. Maybe also useful for the teaching of understanding of the Earth system.
Yeah, I mean, definitely one of the best sort of things I did in undergrad was build a carbon cycle box model. It's hugely informative. So I'd love to sort of teach folks how to do that or help them with their own models.
So you have cooperate with other departments, or you just do by yourself?
It sort of depends on the complexity of the problem. For a lot of the I don't know, how hard is the course going to be? For an intro level course, I can certainly teach people how to build box models, parallelized, isotope-enabled numerical frameworks, and you can do that in R, Python, or MATLAB, sort of whatever software is available. If we're really getting more complicated, it depends on the question for who you want to bring on. For something like seismic inversion, hopefully we can collaborate with some of the existing expertise, because that's really out of my wheelhouse. But anything with isotopes, I can do.
Other questions?
So you would explain kind of how you relate on your involvement with Earth and overall diversity in carbon, how there's a lot of representation. Is there some path or like angle that you have specifically very interested about increasing diversity and representation?
Yeah, so I think there's some sort of low-hanging activities like applying to become an AGU Bridge program partner. There's a couple of universities in Texas that are already part of that system, so to happily lead that program, lead that application process. There's other stuff just like, and maybe you already do this and I don't know about it, but going to national conferences like SACNAS could be a huge step forward, right? And that's really, it's hard to do. It takes a lot of faculty involvement. You have to go to a conference, represent the university, have materials ready, but that's the kind of work that I'm sort of willing to do. So I think that going to some of these conferences, engaging in the discussion, joining the established AGU programs, that would take us a long way forward.
Take her question one step forward. It's great. Why should we hire another white guy?
No, it's a great question. So my thought on this is like, if you have someone who you are comparably excited about, who's going to build an isotopes lab, hire that person. If there isn't someone else you're thinking about who's going to build an Orbitrap-based lab, who's going to run global carbon cycle, biogeochemistry questions, or if you want somebody who's substantially more focused on one particular aspect, right? This works kind of all over the board because that's what the carbon cycle requires. But if you say, look, we want somebody who's going to measure one thing in one system, and especially if they don't look like me, hire that person. That's probably what this field and this discipline needs. That said, if you're interested in this work and that's what you're pumped about, then that's why you would hire me. Anybody else want to shoot straight? I'm on board.
Good question.
So when you were talking about like